Hey folks, this video we're going to talk about angular momentum. We're going to introduce angular momentum. So I will kick it off right away with an equation and a quick explanation. So you can think of angular momentum as how much spin something has. The more massive it is, the bigger it is, and the faster it's spinning, all those would make it have more spin. Okay, it's like a bowling ball spinning at 1 rev per second is going to have more angular momentum than a tennis ball spinning at 1 revolution per minute or per second. So that's the idea. Now, the equation for that, there's actually two equations, okay? The definition of angular momentum, well, first they use an L, which is, I know, a little strange, but they use an L. And the equation for this is R, and here's our cross product, cross P, which is little momentum, okay? The units are, well, you have meters here, and momentum is kilogram meters per second. So you end up with kilogram meters squared per second. And it's an odd unit, and that's just what it is. There's no like shortcut for that as far as I know. Now, the magnitude of the angular momentum is equal to, if we do R cross P, okay, so think about this for a second. Let's say this is a rock that you're twirling on a string. So let's say you're holding the string here, here's the string, and there's the rock. And let's say the rock has a mass m and is moving in a circle. We'll just say counterclockwise, and the radius of that circle is r. Okay. So if we were to calculate this, you'd have r, and then the momentum of that rock would be m times v. So that's your momentum. And right now you'll notice that the momentum, which is perpendicular to the radius, so the cross product is slightly sine of 90, which is 1. So there's no angle to worry about here. So you end up with this. Now, if you look at terms of angular stuff, okay, we have r times m, and then velocity is equal to r omega. So if I gave you the angular velocity of that rock going in that circle, this is how you'd write this. And then I'm going to just rearrange the letters. You get m r squared times omega. Well, what's mr squared? Well, for a point mass, that's the moment of inertia that we've been talking about the last couple chapters now. So it turns out that there are two equations for angular momentum. If you have a point mass, okay, so that would be like a rock going in a circle, okay, then you're going to use the equation L equals R cross P, okay. However, if you have a solid object spinning, like let's say you have a bowling ball spinning or a bowling ball rolling for that matter, then you're going to use L equals the moment of inertia times omega for the object, okay? So for instance, a bowling ball, it's got more mass and usually a bigger radius than the tennis ball, so it's going to have a bigger moment of inertia. So even for the same angular velocity, the bowling ball will have a greater angular momentum, okay? Now, the cross product nature of angular momentum, let's talk about that for a second. And I'm going to focus on the left equation here, the point mass moving. So let's say you are standing on the floor and you're on a turntable, so you can spin, or you're on a spinny wheelchair or something like that, so your body can spin without friction. So let's say here is you, okay, you're an X today, and you are on a spinny chair that's allowed to spin freely without friction. And on the floor, this is a top view of you, so this is like the top of your head, okay, and we're watching you from above. And let's say you push a car. So a car is going to behave like a point mass. And let's say the car is going to the right. And I'm going to look at two locations for the car. We're going to call this location A, and then this location B. Okay. Relative to you, standing here on the turntable, which car has more angular momentum? Car A or car B? And another way to think of that is if you reached out and grabbed the cart, which one would make you spin more? Cart A or cart B? Now we're going to actually throw some numbers on this. let's say this distance here is 2 meters, okay? And let's say this distance here is 6 meters. Okay, now obviously you're not going to reach 6 meters, but let's say you could, okay? You're probably not going to reach 2 meters either, right? But let's say you could. All right, so if we call u the origin, we're saying what's the angular momentum of each of those carts with respect to u. So u are the origin in both cases. So first of all, what's the velocity of the cart? Well, let's say it's 10 meters per second in the I hat direction. Okay, so the cart is moving to the right at a constant 10 meters per second. Let's say the mass of the cart is 1 kilogram, just to keep it really simple. So R1, the first, or R, I'll call it RA. RA is going to be 0 I hat plus 2 J hat meters, right? It's straight up. RB would be this. Okay, so RB would be 6 I hat plus 2 J hat meters. Okay, to figure out the angular momentum, okay, we're going to do R cross P, and we're going to do that for both, and we're going to see which one gives us a bigger angular momentum. Okay, so I'll start with A. So we're going to do what we did in the last video. We're going to do our I, our J, and our K, and we're going to use our vector cross product, and we're going to do R and P, and this would be RA. Okay, RA is 0 to 0, and the momentum of the cart is m times v, which is just 1 times 10, so it's just 10 in the I hat direction. So here we have a 10, and then we have a 0 and 0. Okay, so that's our R cross P. All right, and then we set this up. We have our I's, which is our J's and K's, 2, 0, 0, 0. That's our I hat, and then we have minus. For the J hat, we cover up the J column, and we do 0, 10, 0, 0 in the J, and then plus, and then in the K direction, we cover up the K column. We've got 0, 2, 10, and 0 in the K column. And then we do the plus and the minus for each of these. And in the first one, you get a big fat 0 in the I direction. Then we have minus. Here you're going to get 0 too, right? Because you're taking 0 times 0 minus 0 times 10. So that's also 0 J hat. And then plus, well, here's the one where you finally get a number, right? You get a 0 here. That's a plus. And then this is the minus, which is 0 minus 20 K hat. Okay, so our angular momentum of that cart about u as the axis, is negative 20 K hat, and it would be kilograms meters squared per second. Okay, so that was for A. Now the cool part with B is we don't have to redo this whole entire process. We can just modify. So for RB, all I have to add is a 6I right there. Okay, so where is that going to come into play? Okay, well, remember in the I we did J and K, so it doesn't come into play there. Here we're doing I and K, so it does come into play there. This should now be a 6 right there instead of a 0. And then here we do I and J, so this should also be a 6 instead of a 0. Does it affect our answer at all? Well, no. Right here, when you do 6 times 0, you're still going to get 0. And here, when you do 6 times 0, this is still going to be 0. So it turns out that LA and LB are equal. The angular momentum of this object about this point, whether it's at A or B or anywhere else along that line for that matter, is going to be the same. It's negative 20 K hat units of angular momentum. In other words, in English, if you were to reach out and grab the cart when it was at location A, or if you were to reach out and grab the cart when it was at location B, both would make you spin the same amount in your spinny chair. Okay, so it doesn't matter. What matters, the short answer for this is what matters is the perpendicular distance from your origin to your line of momentum, which is just our 2 meters here. This 6 meters didn't matter one bit. Okay, now I do have one more thing to go over with you here. Okay, and that's leading up. Well, actually, I take that back. I'm going to start you off with that in the next video. Okay, so again, as a summary, you've got 2 ways to calculate angular momentum. You have a point mass. So if you have a rock moving, or in this case, a cart moving along the floor, the angular momentum of it is r cross p. If you have an object spinning, L equals I omega. In the next couple of videos, we will use the right-hand one a lot more. So we'll have some practice with that. So I hope that was helpful, and thank you very much.